And in this week's physics video, we're going to talk about how to find some kinematic quantities using calculus. So in this problem, we're given a velocity vector equation, which is it's v with a vector hat, which tells us that it's got a direction, and in this case the direction is only in the I hat, or the x direction. And it depends on these constants a and b, and it's a function of time. And so our job is to find the acceleration vector at a time equal to t naught, and the magnitude of the displacement. So not the position, but the displacement that happens at a time of t naught. And notice this one doesn't have a vector hat because that's a scalar. And so we're told that at the initial time of 0, the displacement, or rather the position vector of this situation is equal to 4 meters in the I hat direction. So first, let's find the acceleration vector. And we know that if we want to find some acceleration function of time, and we know velocity, then we just have to take one time derivative of the velocity function. And so we're going to say, we're just going to take this derivative, and as a result we'll end up with a times b from the chain rule times cosine of bt. And there's no initial condition to add, but I do need to add an I hat, because I told you it was a vector on the left side, so I have to keep my promise on the right side. So if I just want to find it as at the time t naught now, all I have to do is plug in t naught for t. So if I do that, then acceleration at time t naught doesn't look much different. It's just this. Exactly what we had before, but it's just got a t naught in it now. And you could plug that into your calculator with numbers and all, and it would come out correctly. So now for the second part, we're looking for the magnitude of the displacement. So we're going to do the exact opposite. We're going to integrate it. But we're going to have to remember a little fact, and that is that r of t, or the displacement vector at time t, is equal to r at 0 plus the integral from 0 to t of v of t dt. Or if you want to be fancy, you can make those t primes in order to make your notation a little bit nicer. But we just want to find delta r. And so to find delta r, we don't even need this r naught, because we'll just pull it over to the other side and say that that's the change that we experience. So we're going to move this over, and just as a result, say that the displacement is equal to this function right here. So we're going to say delta r of t is going to equal, in this case, the integral of this function right here. And if we want to do that, we're just going to know that the integral of sine is a minus cosine of bt. The a is going to stick around, and we're going to have to divide by a b in order to make the chain rule work itself out. And then we have to be really careful about something important, and that is to apply these conditions, these bounds from 0 to t. So if we plug in t, we get the exact same thing from before. We get minus a over b cosine of bt, and then we have to subtract 0 plugged in, and when I plug in 0, this cosine goes to 1. So I'm going to subtract negative a over b, or add a over b. And then I don't want to write this out again, so you guys know that I'm just going to add a t naught in for my time to find the displacement at that time. And notice I dropped my I hat. I needed one over here. But when I take the magnitude, I know that the magnitude of the vector in one direction is just equal to the vector itself. So there is still a negative here. And so that's my answer for the second part. That's delta r at time t naught. So